So far this week, in addition to learning how to numerically solve differential equations, we've established the basic rules about why things move. These are Newton's laws. When you have an unbalanced force on an object, it will accelerate. The acceleration is proportional to the net force and inversely proportional to the mass. We also developed an important bookkeeping tool, the free body diagram. The rest of this week will be coming up with examples of situations we can model using the reasoning from Newton's laws. We'll follow a similar trajectory from kinematics, where we learned about position, velocity, acceleration, then applied it to understanding things like projectile motion. We will first consider equilibrium situations, where nothing is moving, so-called static equilibrium, or where the motion is with constant velocity, so-called dynamic equilibrium. We'll develop the tools to understand how the forces are behaving in that situation. Conceptually, it's a pretty clean subject, but the vector nature of forces can make the mathematics tricky. Next, we'll consider the problems where forces are unbalanced, leading to acceleration. We'll then circle back to all the forces we briefly encountered and try to deepen our understanding of them. This includes weight, normal force, ropes, and pulleys. Next week, we'll discuss friction forces and drag. This will give us all the infrastructure we need to solve engineering-type problems, as well as think about some biological processes that go on in cells, or molecular machines do the job of keeping us alive. There are some really great worked examples in our textbook, sections 5.1 and 5.2. I recommend looking at those. In terms of approaching these problems, let's start with discussing equilibrium. When the net force on an object vanishes, we say it's equilibrium. If the net force is zero, then by Newton's second law, the acceleration is zero. The procedure for solving an equilibrium problem has several steps. The first thing we almost always need to do is draw a sketch. Unless you are really gifted with spatial reasoning, you won't be able to keep straight in your mind what's going on unless you draw a picture. You also want to be able to refer to it and show it to other people. The second step is you want to identify the forces. We've had some practice with that already. After we identify the forces, we draw a free body diagram. Remember, a free body diagram consists of a dot with arrows coming out of it representing all of the forces on our object. The next step is that we decompose the forces into components along some axes. So we draw some axes. And this one I drew here had all the forces along the axes. So maybe I'll draw another one. Say we have something like this. In this case, we would want to break this force into two components. And finally, the last step is we calculate the net force along each of the Cartesian directions and set that force equal to zero. The part here, which typically trips students up, the most difficult part, is breaking the forces into components. This is tricky, but it's a learned skill. Anyone can master it. It just takes practice. So again, have a look at some of those work examples in section 5.1 and 5.2. In the following parts of this week, you are going to get plenty of practice with doing these problems, and you'll see some videos of some examples being done. Okay. Some of the problems you'll see are hard, and some are easy. If you're trying to do one of these weekly assessments, and you get stuck, you don't have to spend, an hour banging your head on it. If you just leave that question blank and submit the survey, it'll give you all the solutions, and you can look at that, and then you can reassess your knowledge and try and figure out what you're missing. So this was the structure of how you solve a statics problem. Solving a dynamics problem is actually no harder. The only difference for a dynamics problem is this last step. Instead of setting the forces equal to 0, you set them equal to the components of the acceleration. Again, you'll see some great examples coming up, and you'll have plenty of opportunities to practice.